Mr. Chairman, ladies and gentlemen, I'd like to present my approach to void nucleation problem. Tractographic observations reveal the cause of void nucleations, and in the case of strong homogeneous inclusions, the first stage of void nucleation is debonding of surface of inclusion from the matrix. In a case of weak inclusions, especially if they are a conglomerate of several standard inclusions, the first stage of damage is breaking of inclusion, and then void growth is accompanied by debonding of surface of inclusion from matrix. However, However, we can also find cases in which crack penetrates matrix without any debonding. The problem of void nucleation was taken in many papers. Different factors were analyzed, for example, mechanical properties of inclusion and matrix, distribution of inclusions, their shape, their size, and there are many criterions for void nucleation. They can be summarized by equation created by Argon, in which sigma sub n is hydrostatic stress, sigma sub EQ is Huber-Mises equivalent stress, and Y and X are weight parameters. In my analysis, I use steel for chemical reactor. Main inclusion in this steel are manganese sulfides of size from 1 to 5 microns, and average space between them is approximately 100 micrometers. Mechanical properties of this steel were used to model material of matrix. As far as the inclusion is concerned, I assume that this inclusion is elastic through the whole range of loading, and Young modulus is equal 100 gigapascals. The geometry of model was similar to McClintock geometry. However, instead of void, there was inclusion in the shape of cylinder. The cell was modeled in plane strain, and due to symmetry, only this shaded quarter was modeled. I assume that cell is located in the vicinity of the crack tip in highly constrained mechanical field that sets relations between displacements. The main feature of this model were cohesive zones. There are 3 cohesive zones, and first zone, zone A, models interaction between surfaces of inclusion and matrix. It was created applying surface-based approach, and 2 other zones, zone B and zone C, models cracking of inclusion and matrix. They were created applying element-based approach, but they are located in symmetry plane, so some modifications were needed. The first one, the obvious, is the reduction of total energy of fracture by half. Then initial stiffness of elements were doubled. The nodes creating zones were shrunk to create zero thickness zone, and to avoid uncontrolled movement of nodes connected to symmetry plane in horizontal direction, there were additional constraints. The movement of these nodes were connected with counterparts, partners connected to matrix and material of inclusion. The initial properties of cohesive zone were evaluated using literature data and experimental data. However, those are only initial values and were changed during simulations. In first simulation, to reduce number of parameters, it is assumed that parameters of zone A and zone B are identical, and the value of cohesive stress is equal 1100 megapascals. This value is not accidental, because Berem in one work assumed that this is cohesive stress for manganese sulfide, but in steel A508. And as you can see, this set of parameters leads to breaking of cell. It breaks in the way similar to breaking of homogeneous cell, there is only small protrusion in the vicinity of the inclusion. So, to obtain a situation in which the first stage of damage will be breaking of inclusion and then debonding happen, the parameters for zone A, cohesive stress for zone A was decreased gradually in such a way that critical displacement at which interaction between surfaces vanished will become constant. So it turned out that decreasing of the maximum stress below 69% of cohesive stress for zone C leads to changing behavior of the cell, because the first stage of damage in this situation was debonding of inclusion from the matrix. So in the next stage, the parameters of zone A and B were the same, and they were gradually decreased. Here we have example for 800 megapascals. This is also a characteristic value because Benjamin proposed this value as cohesive stress for zone A in steel A508 for interface between inclusion and matrix. As you can see, this set of parameters leads to a situation in which the first stage of damage was breaking of inclusion, and then void growth was accompanied by debonding of surface of inclusion from matrix. So consequently, decreasing the stress for zone A and for zone B leads to a situation, well, this is another example. Decreasing of stresses below 23% of cohesive stress for zone C leads to a situation in which there was change in behavior of this cell, because the first stage of damage was again debonding of inclusion from matrix. I tried to, let's say, get this situation again in which inclusion breaks and the debonding takes place also. So it turned out that it was easy to get, because it was enough to increase the value of cohesive stress for zone A by 1% of cohesive stresses for zone C. But if you compare value for zone A and zone B, the difference is about 4%. So, instead of conclusion, I put this picture in which there are results of these simulations. As you can see, if the stress for cohesive stress in zone A and zone B is greater than 63% of cohesive stress for zone C, the cell breaks in the way the homogeneous cell would break, but there is only extra feature, this protrusion on the surface of fracture. If the stresses are lower, I mean this maximum stress for zones B and C are smaller, the first stage of damage is breaking of inclusion, and then debonding takes place. The area of debonding is greater for lower values of the stressor. However, for any case, if the stress for cohesive stress for zone A is smaller than cohesive stress for zone B, the first stage of damage is debonding. Well, for lower stresses it is not clear, because for lower stresses it turned out that the cohesive stress for zone A could be slightly bigger than cohesive stress for zone B to get debonding. It is about 4%. Thank you for your kind attention.
Thank you very much. So you are very good at keeping the presentation times. So we have time for a couple of questions. Okay, Kim?
Yeah, I was a little bit surprised about the size of your manganese sulfides, because in the steels we are using, they are generally a magnitude larger and strongly elongated.
Yeah, but this parameter was taken from an article by, let's say, Xiao, Falesberg, and C, as I remember. They describe this structure exactly and say that the manganese sulfides are from 1 to 5 micrometers. I can provide you with this.
I'm just saying that they are surprisingly small to be manganese sulfides. But manganese sulfides are also so soft that the
young modules change from 69 to 168 gigapascals. So I get this average value, approximately average.
or perhaps it was some other type of inclusion. That's also possible.
Yeah, but this is only model.
So I guess I have one question. So in your model, so since the sulfide manganese is soft because of the low elastic,
It has 100 gigapascals, so rather soft.
yeah, compared to the steel. So could it be that actually the main mechanism for depot formation could be the breaking of the manganese instead of debonding of the? Because I understand your model actually takes care of the debonding of the.
Since it is model, it is possible because it depends on the parameters of the zone.
Okay.
But if I have this value of the, let's say, young modulus exact, then we will see what happens.
But the cohesive model does not see the breaking of the sulfide, only the debonding.
Yes.
Okay. Okay. Any other questions? No. If not, okay. I'd like to thank you again.